Hello everyone! Today we will be discussing an important concept in quantum mechanics known as photoelectric effect. In this video, we will explain what is photoelectric effect, the theory behind it, the experimental observations, and its real-life application. The photoelectric effect refers to the emission of electrons from a metal surface when light of sufficient frequency shines on it. When light hits the metal, electrons are ejected instantly if the light frequency is above a certain minimum value called the threshold frequency. This observation could not be explained using classical wave theory, which expected energy to depend on light intensity rather than frequency. However, it was Albert Einstein in 1905 who successfully explained this phenomena using the concept of light particles known as photons. His explanation provided strong evidence for quantum theory and earned him the Nobel Prize in Physics in 1921.
Now, moving to the theory behind the photoelectric effect. According to Einstein, light consists of particles called photons. The energy of each photon is given by the equation E equals to hf, where h is Planck's constant and f is the frequency of the light. When a photon strikes an electron in the metal, the photon's energy is used to overcome the metal's work function, and any extra energy becomes the kinetic energy of the emitted electron. This leads to the Einstein photoelectric equation, Ke equals to hf minus V, where V is the work function of the metal.
From the experiment, there are three case observations. First, no electrons are emitted if the light frequency is below the threshold frequency, regardless of intensity. Second, increasing the light intensity only increases the number of emitted electrons, but not their kinetic energy. Third, increasing the frequency of the light increases the kinetic energy of the electrons.
Let's look at the experimental graph. This is the graph of kinetic energy of electrons against the frequency of the incident light. The straight line shows that kinetic energy increases linearly with frequency. The x-intercept represents the threshold frequency, which is the minimum frequency needed to emit electrons, and the slope of the line is equal to Planck's constant, which supports the idea that energy comes in discrete packets called photons. These observations confirm that the kinetic energy of electrons depends on the light frequency, not the intensity, exactly as predicted by Einstein's photon theory.
What happens when light hits metal? Electrons get so excited, they literally jump off. That's the photoelectric effect. In an evacuated glass tube, a photosensitive plate and a metal plate are connected to a voltage source. Light enters through a transparent window, hits the photosensitive plate, and boom, electrons start flying, creating a current we call the photoelectric current, measured by a microammeter. But what affects this current? 1. Intensity of light. Brighter light equals sign, more electrons equals sign higher current. 2. Voltage on the metal plate. Increasing voltage boosts the current, but only up to a point, called saturation current. Reverse the voltage, and the current drops until it hits zero, the stopping potential. 3. Frequency of light. Higher frequency means more energetic electrons, changing the stopping potential and current. Albert Einstein explained this phenomenon using the idea that light behaves like tiny particles called photons, earning him the Nobel Prize in 1921. Talk about a light bulb moment. If you found this shocking science fascinating, like and subscribe for more.
This diagram shows the experimental setup for the photoelectric effect. The experiment is carried out inside an evacuated glass tube to allow electrons to move freely. Lights enter through the quartz window and falls onto the photosynthetic metal plate, which is the cathode. When the light has a frequency above the threshold frequency, electrons are emitted from the metal surface. These electrons move toward the anode, creating a small electric current. The current is measured using a microammeter. By adjusting the applied voltage, known as the stopping potential, we can determine the kinetic energy of the emitted electrons. The photoelectric effect has many important applications in everyday life. One important application is in solar cells. When sunlight falls on a solar cell, the photoelectric effect allows photons to transfer their energy to electrons in the material. These electrons then move through a circuit, producing electrical energy. Another application is photoelectric sensor, such as those used in automatic doors. When light falls on the sensor, the photoelectric effect produces an electrical current. When a person interrupts the light beam, the current changes and this signal is used to open the door. The photoelectric effect is also applied in light meters and camera sensor. When light strikes the sensor, electrons are emitted and produce an electrical signal that depends on the light intensity. This allows camera to capture image and light meter to measure brightness accurately. This example shows how quantum physics is used in everyday technology. In summary, the photoelectric effect demonstrates that light behaves as particles called photons, which can knock electrons out of a metal surface. The energy of the emitted electrons depends on the frequency of the light. No, it's not intensity. Light with a higher frequency produces electrons with greater kinetic energy, while lower frequency light cannot eject electrons at all. This discovery challenged classical physics and confirmed the foundation of quantum mechanics, providing strong evidence for the particle-like behavior of light. Understanding the photoelectric effect has also led to many technological applications, including solar panels, photoelectric sensor, cameras, and automatic doors, showing how quantum mechanics impact modern technology in everyday life.